Swayam Prabha. Digital India. Educated India.
Hello everyone, we are going to begin with module 7 and today we are starting with lecture 1. In the lecture 1 today, we are going to cover the concepts such as the anisotropic earth structure, lattice and shape preferred orientation anisotropy, transverse and azimuthal anisotropy, anisotropy of the upper crust due to cracks, and then we will be seeing how the anisotropy is generated due to the minerals and the rock. Finally, we will be having the summary of today's lecture. Before we move on to the topics of today's lectures, let's have a recap of what we have learnt in the previous module, that means the module number 6. In the previous module, we learnt that the ray parameter for the spherical earth can be given as P is equal to R sin I by V, and the ray path, travel time and angular distance for the spherical earth can be expressed as travel time as a function of ray parameter, that can be written as the integral of the elementary distance divided by the velocity, that is equal to twice of the one-way travel time, integral from the bottoming depth to the depth of the hypocenter, eta square dr divided by r, zeta square minus p square to the power under root, where zeta is equal to r by v. Then we can also find out the epicentral distance as a function of ray parameter, that is equal to the integral of d theta, that is further equal to 2p integral bottoming depth to the depth of the hypocenter, dr by r in bracket eta square minus p square to the power under root. For triplication, the back branch meets the two forward branches at 2 points on the travel time and the p delta curve. For triplication, dp by d delta should be equal to infinity, or you can say it should tend to infinity. We also learnt about Herglos-Wechert integral, and it is an approach which gives the distance travelled by a ray with ray parameter p as a function of velocity structure, and this particular integral can be used for the inversion of travel time curves, and hence it can provide an idea about the velocity variations within the earth. So it can be expressed as delta as a function of ray parameter, that is equal to 2p integral from the bottoming depth to the depth of the hypocenter, that is dr by r in bracket zeta square minus p square to the power under root. Then we learnt about the travel time data that are generated by combining from numerous earthquakes at epicentral distances from different earthquakes. Then we also learnt about the different phases and their nomenclature, and in the nomenclature we learnt that the name of the particular phase can give us an idea about the travel path where the particular phase has traveled through. And then we have seen some surface reflections such as PP and SS, and we know that most of the phases that we record on our seismogram are the minimum time phases, and as per the Fermat principle, the phases that we record, the travel time associated with that should be extremum, and in case of most of the phases it is minimum, but in case of the surface reflections such as PP and SS, these are the maximum time phases, in contrast to reflection phases like SCS, which are minimum phases. For the core, the shadow zone occurs for distances between 98 degrees to 145 degrees, which means no direct P wave can be recorded within the epicentral distance of 98 degrees to 145 degrees, and seismic energy also enters the shadow zone via P and S wave that diffract around the core. As I told you, direct wave cannot be recorded into the shadow zone, but the diffracted energy of S and P wave and also the multiples of P and S wave from the surface can be recorded in the shadow zone. The K denotes passage through the outer core, because the shear wave cannot travel through the liquid. As it enters, then it converts to the K wave, and then reflection of the core mantle boundary are denoted by lowercase c, and P wave in the inner core are denoted by I. Similarly, the S wave in the inner core is denoted by J, and as I told you in the previous module that the J phases are generally weaker on the seismogram and they comes later onto the seismogram. That's why they are very rare to record. And then we learnt about the various sections of the earth, that means the subcrustal lithosphere, asthenosphere, and we saw that the subcrustal lithosphere is characterized by the high P and S wave velocity about 8.1 and 4.5 km per second respectively. It is approximately 0 at mid-oceanic ridges and have around 200 km beneath the stable craton. Across the entire earth, there is a low velocity zone beneath the lithosphere that coincides with the expected mechanically weak asthenosphere underlying the stronger lithosphere. We also learned that the velocity differences between the crust and the mantle mainly results from the different compositions. The velocity discontinuities we also see at around 1410 km and 660 km that are lying in the upper mantle, and that is marked as the transition zone between the upper and the lower mantle. Upper mantle travel times show 2 triplication because of the presence of the 2 transition zones at 410 km and 660 km where the velocity rapidly increases. So because these are the high velocity zones, so as per our ray theory, there should be triplication, and these 2 triplication occurs at around a distance of 15 degree and 22 degrees caused by these discontinuities. At the very bottom, that means at the very bottom of the mantle, there is another layer that is a very ultra low velocity zone that is of a thickness of around 10 to 20 km. D double prime layer is also present at the base of the mantle, which is a fascinating and poorly understood region and show strong evidences for significant seismic anisotropy. So this was the recap of the previous module. Now let's start with today's lecture, where we are going to first learn about the anisotropic earth structure. If you remember, so far we have been considering the earth as an isotropic material, and then we have been deriving various formulas associated with the seismic waves. And when we were considering the earth as an isotropic material, then the elastic properties in the isotropic material are same in all the direction. And we also considered the Hooke's law, which relates the stress to the strain, and the proportionality constant is the stiffness tensor that is represented by capital C in subscript I, J, K and L, where I, J and K and L all are varying from 1 to 3. So a total number of elastic constant that this particular tensor will possess are 81. So as per the Hooke's law, sigma ij is equal toCijkl EKL, and in such materials the stress are linearly proportional to the strain via Hooke's law, and as I told you, it should contain 81 number of elastic moduli, and we can reduce these 81 number of elastic moduli to 2 after applying some symmetries and after considering the isotropy. And after we consider all those symmetry of the energy and the symmetry of the strain, then what we can do, we can reduce those 81 number of the elastic moduli to 2, and it will be termed as lambda is mu. These are also known as the Lami's parameter, and mu is the shear modulus. On the other end, when we are talking about the anisotropic material, where the physical properties are changing with direction, in fact, anisotropic material also follows the Hooke's law, and it involves more than 2 elastic constants, and it can have up to 21 independent elastic constants. So all in all, what we can say, if a material is having more than 2 elastic constants, then it can be anisotropic. In the figure, what you can see is that there is a S wave that is propagating in the isotropic material, or you can say it is starting off from the isotropic material. As soon as it enters the anisotropic material, then it gets split into its two components, S1 and S2. Both are orthogonal to each other, and one component, that is S1, is having the faster velocities than the S2 component. So as it moves, then it gets further away from the S2 component, and after it comes out into the isotropic material, then these two components will be recorded at the seismometer at the surface. So what is the takeaway from this figure is that anisotropic material basically split the shear wave into two orthogonal components, and one is transverse and another is radial component, and the transverse component travel faster, so it will move away from the radial component, and then it will move on further in the anisotropic material. After they come out, they will basically follow the same path. Now let's talk about why the anisotropy occurs, and in that particular topic we are going to talk about lattice preferred orientation anisotropy. In short, it is known as LPO. And there is another anisotropy that we can talk about is shape preferred orientation anisotropy. So lattice preferred orientation anisotropy basically occurs due to the inhomogeneity of the material, or you can say this inhomogeneity is happening in the material because material is non-uniform, or you can also term it as heterogeneity. And one of the anisotropic material that is present in the upper mantle is olivine, and the mineral olivine is homogeneous in that it is composed of the same repeating group of the atoms, but acts anisotropically because it aligns itself in the direction of the mantle flow. So what basically happens, the olivine crystal has two kind of axes, one is faster axis, one is slow axis. So because it is present in the upper mantle, so when the deformation happens in the mantle, then it aligns its fast axis along the direction of the mantle flow, or you can say in the direction of the deformation. So if you look at this particular crystal, that is the olivine crystal, and this is the acrystallographic axis of the olivine crystal. So when there is a deformation in the mantle, then it basically aligns this acrystallographic axis in the direction of the mantle flow. So which basically is responsible for the induction of the anisotropy into the upper mantle, because the olivine crystal is preferentially orienting itself into the direction of the mantle flow. And if you generally talk about the crystals or other minerals are randomly oriented, so it basically produces weak anisotropy. Is the olivine crystal that is basically orienting itself into a preferred direction, then it may produce a higher amount of anisotropy into the upper mantle. Now let's talk about shape preferred orientation anisotropy, that is in short known as SPO. And you can understand that a common situation is when the material has directionality in its structure, and seismic waves travel with different speeds parallel and perpendicular to the layers, and this situation is known as the shape preferred orientation anisotropy. So if you look at this particular figure, then this is the seismic reflection profile and the cartoon of the crust, and either you move in this direction or in this direction, then both either in the perpendicular or the parallel direction to the layer, the seismic waves will travel at different speed. So that is why it is known as shape preferred orientation anisotropy. Now before we move on further, let's understand what is the white matrix. And in the white matrix we can have the stiffness tensor that is represented by C subscript IJKL, that is a tensor quantity, and we are going to represent this CIJKL as CMN, and where the indices M and N will vary from 1 to 6. So for example, if suppose there is 1, 1, then it can be written as 1, 2, 2 can be written as 2, 3, 3 can be written as 3, 2, 3 can be written as 4, 1, 3 can be written as 5, and 1, 2 can be written as 6. So when we are mapping these I, j to M and k, L to N, then we can write CIJKL as CMN. So if you consider this particular stiffness tensor, which is represented by this very big matrix, then in terms of white matrix, if we want to represent it, then it will look something like this. It is little smaller than the previous one. So for an isotropic material, if we want to represent this matrix in the form of white matrix, then it can be looking something like this. So in the form of isotropic material, where only two elastic moduli is possible, that means lambda and mu. So this white matrix will be in this form. You can see there are the components that are represented in the form of lambda and mu. So that is what it is written. For an isotropic material, the CIJKL tensor can be written in terms of two independent elastic constants, or the white matrix for the isotropic material may look like as following. So this is the particular expression for which write the stiffness tensor for the isotropic material in the form of lambda and mu, where delta is the Kronecker delta function. So as I told you, delta Ij will be equal to basically 1 when I is equal to j, and it will be equal to 0 when I is not equal to j. So this is the Einstein summation expression for the stiffness tensor for the isotropic material in the form of lambda and mu. We have seen this equation previously in our first module, and as I have said earlier, this particular white matrix is for the isotropic material in the form of lambda and mu. Now let's talk about transverse isotropy and azimuthal anisotropy. First we will be talking about the transverse anisotropy, and it is also termed as radial anisotropy or axis symmetry and cylindrical symmetry, which basically happens due to a stack of the layered material such as the plywood. So it is a isotropic within the layer, but the properties changes between layer. As you can see, the plywood also a stack of several layers. So elastic properties and hence the seismic velocities of the stack as a whole are identical regardless of the amount of rotation about the axis of the symmetry, which is perpendicular to the layers. However, these aggregate properties differ in the perpendicular direction. So you can see that there are the two direction of the propagation. So this is your x3 axis, this is x1 axis, this is x2 axis. If the wave is traveling in this direction, then it will be having the same velocities in this direction. And if it is having the direction parallel to the x3 axis, then it will be having the velocities different in the x1 and x2 plane, and basically will be showing the anisotropy, and that is known as the transverse isotropy. So a transverse isotropic material are represented by 5 independent elastic constant, that is A, C, F, L and N, and these letters are Beck's notation. These are also known as the Beck's notation. And if the axis of symmetry is x3, so the properties in that direction differ from those in the x1 and x2 plane. The elastic constant matrix becomes this white matrix for the transverse isotropy in the x3 direction will be something like this, and where you can see there are the 5 independent elastic coefficient A, C, F, L and N, and these elastic constant can be understood by this, like A is basically lambda plus mu, and that is in the x1 direction. N is mu, that is x2 direction. L is mu, that is in x3 direction. And this matrix particularly gives the velocities of the waves propagating in different direction. So in the x1 and x2 plane, Vp1 will be A by rho to the power under root, Vs1, that is the shear wave velocity, N by rho to the power under root, and Vs2 is equal to L by rho 1 by 2. So in x1 and x2 direction, the anisotropy is occurring because the shear wave velocities are different, and in x3 direction these shear wave velocities will be equal, although the p wave velocity will remain same. So basically in the x3 direction there will be no anisotropy. So in the x1 and x2 direction there will be anisotropy, that will be termed as transverse isotropy. The horizontally layered earth structure shows transverse isotropy about a vertical axis. The SH wave velocity S1 is generally faster than the SV velocity because the SH displacement is preferentially in the first layers, whereas SV samples both equally. So SH will be having the faster velocity, as you can understand from the surface wave, which has the two types of the rays, that are the love waves and the Rayleigh waves. And love wave is basically made up of the SH wave, and Rayleigh wave is made up of the SV wave. So the velocity of the love waves will be obviously higher than the velocity of the Rayleigh wave. The transverse isotropy is often characterized by three parameters, that are zeta, phi and neta, and this zeta is equal to a capital N by L, that is further equal to S1 by S to the power square. Phi is equal to C by A, P1 by P2 square. Neta is equal to F upon A minus 2L. If the material is isotropic, then all these parameters are equal to each other, that is further equal to 1. And in case of the layered structure, which basically produce anisotropy, in that case zeta will be greater than 1 and phi will be less than 1. Now let's start with the azimuthal anisotropy. So this is a second common type of anisotropy, which is also termed as azimuthal anisotropy, in which the velocities vary as a function of horizontal directions. So one way to obtain this is to have the transverse isotropy with x3 axis turned to horizontal, which is analogous to the extending plywood vertically. So this is the situation. You can see this, these stack of the layers has been extending up vertically, and then the x3 direction is becoming horizontal, and this is the direction of the propagation. And you can understand that as you go either in this direction or in this direction or in this direction, the ray is going to experience different velocities. So that is why it is known as azimuthal anisotropy. And the p velocity varies with azimuth as this, which depends upon the value of the azimuth, that is theta, that is equal to a1 plus a2 cos 2 theta plus a3 sin 2 theta plus a4 cos 4 theta plus a5 sin 4 theta. And this 4 theta component is very small and is often ignored in the teleseismic studies. And the values of a1, a2, a3 and a4 and a5 depend upon the 21 elastic constant that basically generates the anisotropy in a material. Now let's talk about the anisotropy in the upper crust due to the cracks. So the upper crust is consisting of so many cracks and the joints, and those are responsible to produce anisotropy in the upper crust. The anisotropy in the upper crust will be a function of epsilon, and which is related to the crack density, which is given by n a cube by v, where n is the number of the cracks in a volume v and a is the half width of the cracks. So the Voigt matrix for the stiffness tensor can be written in this form. You can see that the mu value has been reduced by an amount of epsilon. So all other parameters are remaining same. So crack may reduce the shear modulus. If the fluid is incompressible, P wave velocity won't be affected, but S wave velocity will see some change. Now the topic that we want to discuss about is anisotropy of minerals and rocks. An important source of anisotropy is minerals that are anisotropic due to their crystal structure. At microscopic level, the anisotropy can be enormous with velocities along different mineralogical axes, varying by more than 100%. However, the anisotropic grains are randomly oriented, leaving only weak anisotropy, and in some cases the mineral grains are aligned, causing significant anisotropy. The magnitude of anisotropy can be characterized by a small letter k, that is the magnitude of anisotropy, and that is equal to the maximum velocity minus minimum velocity divided by mean velocity. So in case if we are going to calculate the magnitude of anisotropy for the olivine crystal, so for P wave in the olivine crystal, the maximum P wave velocity that we will observe in olivine crystal will be equal to 9.89 km per second. The minimum velocity in the olivine crystal along the slow axis will be 7.72 km per second, and the mean P wave velocity will be around 8.81 km per second. So the magnitude of anisotropy, if we will calculate using this formula for the olivine crystal, which is a major constituent of the upper mantle, then this K will become equal to 25%. That means there is 25% anisotropy for the P wave velocity in the upper mantle due to olivine crystal. The maximum and the minimum shear wave velocities in the olivine crystal are 5.53 km per second and 4.42 km per second. And when we calculate the magnitude of anisotropy using the formula above, then it will come equal to 22%. Minerals range from nearly isotropic to extremely anisotropic, and one of the most isotropic mineral that is present on earth is the garnet, and for the garnet the value of magnitude of anisotropy for P and S waves are only less than 1%, while sheet silicates like mica has the values of magnitude of anisotropy up to 60% for the P waves and around 116% for the S waves. So that is quite large. There are some points that we must remember in the context of anisotropy of minerals and the rocks. So a major factor controlling a rock's anisotropy is the anisotropy of the minerals composing it and their relative proportions. Another important factor is the presence of deviatoric stresses, which can cause a preferred orientation of anisotropic mineral grains that might otherwise be randomly distributed. Crystals are generally oriented with their smallest widths in the direction of maximum compression. Shear in a preferred direction can also recrystallize different mineral assemblages. So the resulting anisotropy reflects a combination of the preferred orientation of anisotropic material and the presence of laminar structure. If we talk about anisotropy of the composite structures, there are further some points that we must remember. Anisotropy can also result from an asymmetric combination of material. The upper continental crust often contains horizontally layered sedimentary rocks. Similarly, oceanic crust is comprised of sediments overlying layers of basalt and gabbro. Such layering can yield transverse isotropy with the symmetry axis oriented vertically. On a regional scale, plate collisions often cause significant metamorphism, sometimes yielding transverse isotropy due to preferred orientation of the foliation of gneisses and schist. As far as the summary is concerned for the today's lecture, it goes like this. Any material in which more than two elastic constants are needed is called anisotropic. Minerals and rock comprises anisotropy either due to the lattice preferred orientation or shape preferred orientation anisotropy. In short, they are known as LPO and SPO. Transverse isotropy is often characterized by three parameters, that is zeta, phi and neta, and their values goes like this. Zeta is equal to n by L is equal to S1 by S2 whole square. Phi is equal to C upon A, that is further equal to P2 by P1 to the power square, and neta is equal to F upon A minus 2L. If the material is isotropic, then all these parameters are equal to 1, and if it is a layered structure like for the transverse isotropy, then zeta will be greater than 1 and phi will be less than 1. In general, the P wave velocity for the azimuthal anisotropy, the P wave velocity varies with azimuth and can be represented as something like this, where A1, A2 and A3, A4 and A5 depends upon 21 elastic constants, and the 4 theta is very small and we consider is almost negligible in case of teleseismic studies. The magnitude of anisotropy can be characterized by small letter k, and that is further equal to the maximum velocity minus minimum velocity divided by mean velocity. And these are the references of today's lecture. We will meet in the second lecture of module 7. Thank you so much. Bye bye.